viewers, welcome to my YouTube channel. It's your number one tutor on this channel, the Science Demystifier. In today's video, I'll be teaching you hybridization in carbon atom. Now remember, we have four main atomic orbitals, that is the sp-d-f orbitals. But the scope of this lesson is restricted to what? sp hybridization only. But before I go further, let me show you the electronic configuration of carbon at ground state. So let's go to the board. Alright, so carbon has atomic number of 6, meaning that we have 6 electrons in the atom of carbon, and that is what we shall be using for its configuration. Now the type of configuration I'm going to be using here is the orbital diagram, the one that involves orbital diagram. Okay, now we simply use rectangular boxes to show energy levels. Okay, so the first energy level which we know is the K shell as 1s, and then the second energy level, which is the L shell, has the second S and the second P. And now remember that the second P is of higher energy than the second S according to Abel's principle. Okay, so electrons must first of all enter into orbitals of lower energy before entering into orbitals of higher energy. Okay, now the P orbital, we all know, has 3 magnetic degenerates, and they are the px, the py, and the pz. Okay, so I'm going to divide the p orbital into 3 so that I will have px, py, and the pz suborbitals. Okay, now since I have 6 electrons, I will now follow the Abel's principle, starting with orbitals of lower energy. So first of all, we'll go to the first S, drop 2 electrons. Before I will now take the remaining 4. Remember, carbon has 6 electrons, don't forget that. Okay, so we'll take the remainder to the second S, where we'll drop 2. Then when I come to the p orbital, there is a rule that is called Hund's rule. In Hund's rule, it states that electrons in a degenerate orbital, like the p orbital that has magnetic degenerates, orbitals are first singly filled before pairing. So I'm going to be filling singly before I start pairing. Now supposing I have more of the electrons, I would have gone to the pz to add 1. Then I will now come back to the px to start pairing. But since my electrons are exhausted, so I will stop at the py. Now one thing to observe in this configuration is that the pz orbital is what? Vacant. So this orbital is vacant at ground state. So when carbon is at ground state, the pz orbital is vacant. Okay, but in excited state, one of the 2s electrons here is promoted from this point to occupy the empty pz orbital, so that at the end of the day, the valence shell of electron will have this configuration at excited state. The valence shell of carbon will have this configuration 1, 1, 1, 1. So remember, this is the px, the py, and the pz. So one electron has been promoted from this point to the vacant pz orbital. Okay, all right. So this is the state at which carbon can hybridize. When carbon is at a excited state, that is when it can hybridize. Now, what is hybridization? Hybridization is the mixing of pre-existing atomic orbitals to form new set of orbitals with the same energy level. I'll be back shortly. All right, now there are three main types of hybrid orbitals that carbon forms. The first one is the sp3 hybrid orbital. Now, what happens during the sp3 hybrid formation? It simply means that carbon uses the electron in the second s, the three electrons in the px, py, and pz orbitals to form covalent bonds. So when carbon uses all the electrons in the second s, the px, the py, the pz orbitals to form bonds, that is when we say to have sp3 hybrid orbitals. So as you can see here, so remember that bonding only takes place in the valence shell, okay? So we have this to be the valence shell of carbon atom. So this is the second s, and it's px, here is py, and then this pz, okay? So remember we have electrons, one single electron each in each of these orbitals. So carbon uses one from the second s, and then the three p electrons to form bonds. So when you combine the three, you have what we call sp3 hybrid. I hope you get what I'm saying. And because we have one electron from the s and three electrons from the p, so we're going to have something like a tetrahedron at the end of the day. So the electron clouds formed at the end of the hybridization looks like a tetrahedron. So when you have, lobes, in these four directions. Okay, so that is why in alkanes we have, of course alkanes are saturated hydrocarbons, so they have single covalent bonds. Okay, in alkanes we have this type of structure where carbon, each carbon atom is surrounded by four covalent bonds, so which results from the sp3. So the sp3 means one electron from the s and three electrons from the p, forming covalent bonds. So that is what we call sp3 hybridization. Okay, now the bond angle between one bond and the next adjacent bond is exactly 109 degrees 28 minutes. 109 degrees 28 minutes. Okay, so remember I said that sp3 hybridization is unique to alkanes, that is the saturated hydrocarbons called alkanes, because they have single covalent bonds and they have this shape which is a tetrahedron. And you get what I'm saying? Alright, so I'll be back shortly. Okay, welcome back. Now, single covalent bonds are formed when two adjacent carbon atoms join their electron clouds together. When they merge their electron clouds, we'll now have what is called covalent bond. And that type of covalent bond is called a sigma bond. Now, sigma bond results from the overlap of the electron clouds of hybridized parts of the adjacent carbon atoms. For example, supposing I have a carbon atom, like this, and I have another one adjacent to it, and I now have an electron cloud coming out from this direction and an overlap of another electron cloud coming out from this adjacent carbon atom. So the resultant effect of this will be a single covalent bond joining two adjacent carbon atoms together, and I said this bond is called a sigma bond. This is a sigma bond. Okay, now what about hydrogen atoms? Surrounding, like in the case of hydrocarbons, where hydrogen atoms are bonded to these carbon atoms. Now remember that hydrogen has one electron, and this electron is in the 1s, that's the first s, which is in the case shell. So if each carbon atom is to pair with hydrogen, this is what happens. So you have the carbon atom having the lobes, the electron clouds, in this manner, like in the case of methane. Then the hydrogen will now come to at this point. So this is assumed to be the hydrogen, with the s orbital. This is the s orbital, okay, from the hydrogen. So the hydrogen comes in at this point, overlapping with the electron clouds from the carbon atom. And at the end of the day, you have carbon atom at the center surrounded by 4 covalent bonds linking hydrogen atoms in this form. Alright, now next is sp2 hybridization. Now in sp2 hybridization, carbon uses the 1 electron in the 2s and the 2 electrons in the px and the py or suborbitals to form chemical bonds, giving rise to a hybrid orbital that is known as sp2 hybrid orbitals, while the pz orbital is left unhybridized. So let us see the pictorial representation of what I just explained to you now. Okay, let's see. If you have this to be the valence shell of carbon atom, then I have here to be the 2s section, and I have this compartment of the p orbital, which is px, py, and pz. And remember that at the excited state, each of the sections is occupied by 1 electron. Okay, each of the sections is occupied by 1 electron. So during sp2 hybrid formation, the bond covers this region. It covers this region. So that's why we have sp2, meaning 2 electrons from the p plus 1 electron from the s is used in the bond formation. So that is what we mean by sp2. And then the carbon atom having this type of hybrid is going to be like this, having 3 electron clouds, surrounding it in this manner. Okay, and then the pz orbital, which is the unhybridized part of the carbon atom, is this side. That's the one I used broken lines to show. Okay, so this is your pz, the unhybridized orbital of the carbon atom. So while we have this to be the sp2 hybridized orbitals. Okay, so at the end of the day, you're going to have a trigonal, sort of shape. Okay, this is trigonal, and the bond angle between one sp and the next, that is one covalent bond, and the next adjacent covalent bond is exactly 120 degrees. That is the bond angle between one covalent bond and the next adjacent covalent bond. And don't forget I said the pz orbital is unhybridized. Now let us see what happens when 2 adjacent carbon atoms are made to sit together in such a way that there is an overlap in their electron clouds. So let's see. Now supposing we have 2 adjacent carbon atoms. Suppose we have 2 adjacent carbon atoms in this manner, and we have the hybridized parts and the unhybridized parts. The unhybridized region of the carbon atoms. So remember that the hybridized parts are simply the sp2. That's where we have the region of hybridization is this point. Then this is your pz of the 2 adjacent carbon atoms. So there will be an overlap of the hybridized parts, giving rise to a sigma bond. So when these 2 electron clouds from the hybridized part of the 2 carbon atoms overlap, there will be the formation of a very strong bond called the sigma bond. Then the overlap of the of the unhybridized parts of the carbon atom gives rise to what we call the pi bond. So in this case, I should be expecting two covalent bonds, and one of the covalent bonds must be a sigma bond and the other one must be a pi bond. And this is common to a set of hydrocarbons known as the alkenes, because in the alkenes you see double bond. They are characterized by what? The presence of double bonds. So don't forget what I said earlier, that the bond angle between one covalent bond and another adjacent covalent bond in sp2 hybrid orbital is exactly 120 degrees, and they have a trigonal shape. So let us see the next one, which is the sp. All right, now the next thing we shall be looking at is formation of the sp hybrid. Now, I believe following the trend of what I've been explaining to you, you will know what you can now use your own discretion to know what will happen in the formation of sp hybrid orbital. So let us look at the valence shell of carbon atom again. So this is the second S, this is the Px, the Py, and the Pz. And then here, hybridization stops at this point, where you have hybridization stops right at this point. So it is only one electron from the S and one electron from the P that will give rise to this type of hybrid, which is called sp hybrid orbital. So the sp hybrid is this part. Then the px orbital is unhybridized, and also the py or the py here is unhybridized, and the pz also is what? Unhybridized. So the electron cloud surrounding a carbon atom that that has this type of hybridization, the electron cloud surrounding the carbon atom will be in this manner. So we have supposing this is the carbon atom, so it's going to be like something like this, okay, because we have only S and P in this direction. Then what happens? There is a region also around the carbon atom, a region of unhybridization, which is here. So that's why you have the P, Y, and the PZ. So while the P, SP, you have SP. So now, assuming we have two carbon atoms, like I said earlier, sitting adjacent to each other, what will be the effect of the overlap of these electron clouds? Now, but before I explain that, or before I show that on the board, I want to tell you that the bond angle between these hybridized, parts of the carbon atom, that is the covalent bond formed here, the bond angle is exactly 180 degrees, and the shape of the molecule is linear in shape. And this type of hybridization is common to the alkynes, and we know that alkynes are unsaturated hydrocarbons characterized by the presence of triple bond. Alright, so when you have two carbon atoms sitting close to each other, the overlap of the three distinct regions I just mentioned, that is the P, Y, the PZ, or this one, the PY, the PZ, or this one, and then we have the hybridized parts, of the carbon atoms. So the overlap of 1, 2, 3 gives rise to triple covalent bonds. 1, 2, 3. Triple covalent bonds. So out of these three triple covalent bonds, one is the sigma bond. This is the sigma bond, while the other two are pi bonds. The pi bonds are formed by the overlap of unhybridized parts of the atom. I hope this explains all that you need to know as far as hybridization in carbon atom is concerned. So if you have any question, if you're still confused about the explanation, please let me have it right there in the comment section. Please don't forget to subscribe to this channel, turn on the bell notification for more updates. Thank you and God bless you. See you next time.